Let us get started. So in the last class, we spoke about the advection dispersion equation and the analytical solution for the advection dispersion equation, which looks something like this. What you see on the screen. Now, remember that this equation, this analytical solution, is for a continuous source, right? So this continuous source has got a concentration of C naught and at x equal to 0. And if that continuous source is maintained for all time t, t greater than 0, then the solution will look something like this. And I spoke about this complementary error function, which is basically an indefinite integral, which you just solve. And so the argument for that in this case, the first term has x minus vt divided by 2 under root dt, where d is the diffusion dispersion coefficient. And then the second term has got the complementary error function with the x plus vt instead of x minus vt, right? So that's the two terms. And then there's an exponential term over there, vx by d and so on. Okay. Anyway, so basically the idea behind the analytical solution is to allow us to come up with um, um, an expression for the concentration at any point in space and time, given the input concentration is or the incoming concentration is C naught. Now, you will notice that in the boundary conditions for this particular problem, C at 0 comma t, which is C at x equal to 0, and for all time t greater than 0, the concentration is specified as C naught. And then the other boundary condition is an infinite boundary condition, C at x equal to infinity, which means at some large distance. And for all time t, the concentration is assumed to be 0. So at a very large distance away from the source, the concentration is assumed to be 0. Now, for an analytical expression, this works perfectly fine, right? But when you want to solve this problem numerically, this infinity poses a challenge, right? So obviously, when you're solving it numerically, we can't specifically mention a value of x equal to infinity, right? Because a domain has got to have some boundary, right? So infinite boundary cannot really exist in the numerical domain. So there are some ways of getting around that in the numerical solution. So we'll talk about that next. Okay, but before we get to that, let us just spend maybe a couple of minutes on the Taylor series expansion. Now, this is a refresher of the Taylor series expansion, and you will see how this helps us with with solving this particular problem. Okay, so just keep in mind that our original equation, let's just go back a couple of slides. Yeah, our original equation is of this form: dou c by dou t equal to minus Vx dou c by dou x plus d, the dispersion coefficient, times dou square c by dou x square. So we have simultaneously one time dependent term on the left hand side, dou c by dou t, a time gradient, and then dc dou c by dou x, which is the first derivative, and then dou square c by dou x square. So you have the spatial derivative, you have both the first and the second order terms. Okay. Anyway, so let us talk in general about the Taylor series expansion. So Taylor series expansion looks something like this: f of x plus delta x is simply f of x plus f prime x into delta x divided by 1 factorial, which is 1 plus f double prime x, which is the second derivative, into delta x square by 2 factorial plus terms of order delta x cube, right? So you can keep writing this up to infinity. So again, we'll just cap it off with the second term, right? So this is my first equation. So if I know the function at location x, and I want to know the value of the function at some small distance away from x. So I know f of x. I want to know what f of x plus delta x is. The way to compute that numerically is by using this expression, right? If I know delta x, I can simply compute this, put in the respective terms into this equation, and that will give me the value of the function at x plus delta x, assuming it's a continuous function and so on and so forth. We'll not get into all of that. Okay, so this is the expression for f of x plus delta x. Now, if I want to know what is f of x minus delta x, it will look very similar to this. It will look like this: f of x minus f prime x into delta x by 1 factorial plus f double prime x into delta x square by 2 factorial plus, minus order of delta x cube terms. Sorry. Right. So this is what the um, equation is going to look like. Okay. Now, from this, you can arrive at several interesting conclusions. The first thing that we did, we've already spoken about this in the context of um, evaluating dou h by dou x and so on earlier, right? So you can simply take the first equation, for example, and you can write f prime x. F prime x, you can write it as f of x plus delta x minus f of x divided by delta x, right? Of course, you are ignoring all the terms delta x square and higher order terms. Those will become smaller and smaller and smaller. As delta x becomes smaller, delta x square, delta x cube, delta x power 4, and so on, those are all relatively small. So the error is of the order of delta x. Okay. So f prime x is simply f of x plus delta x minus f of x divided by divided by delta x. You can also write it as, so this is one way of writing it. Okay. Another way of writing it would be f prime x. You just take the second equation, right? In the second equation also you have an f prime x, but instead of writing it as x plus delta x minus x, you will write it as follows. It will be written as f of x minus f of x minus delta x divided by delta x. Right, now these two expressions that we have written, right, they are pretty identical. Okay, in one case you are evaluating it at x plus delta x and x, and in the other case you are evaluating it at x and x minus delta x. So it's symmetric in that sense. Now the first equation that I wrote, this one, let's call this equation 1 and let's call this equation 2. Now equation 1 is called the forward difference, right? Because you are taking, you're calculating the derivative by using the forward difference, by using f of x plus delta x, forward difference, right? And the second equation is referred to as the backward difference scheme. So the first expression, equation 1, is the first derivative using the forward difference scheme, and the second equation is computing the first derivative using the backward difference scheme. Both of them are equally accurate in terms of their error, the magnitude of the error. Okay, both of these terms are equally accurate. Now there is also another way of doing this, which is called the central difference. Okay, which is basically, what you can do is, suppose I subtract the okay, let's maybe I'll call this equation A and equation B. Suppose I do A minus B. What will I get? On the right hand side, I'll get f of x plus delta x. Sorry, left hand side, I'll get f of x plus delta x minus f of x minus delta x. Okay, so I'm going to write that over here: f of x plus delta x minus f of x minus delta x. Okay, now when I subtract a and b, this f of x and this f of x will cancel out. Here I have f prime x into delta x, and then I have minus f prime x. So when I subtract b from a, I'll get 2 times f prime x into delta x. Okay, and then this term will get cancelled out. This is a plus term, this is plus. So when I subtract when I do a minus b, this will get cancelled out, and then the higher order terms anyway will cancel out. So in other words, I can write this f prime x will be f of x plus delta x minus f of x minus delta x divided by 2 delta x, right? You can do the algebra. Okay, now this is called the central difference scheme. Now the central difference scheme has got one major advantage, in that the error in this in equation 1 and 2, the error is of order delta x. In equation 3, the error is of order delta x square. Okay, I will leave the math to you. You figure out why the error is of order delta x or delta x square in these two. Okay, that's not our main goal of interest. Okay, anyway, so now if I do a minus b, I get this another expression for the same f prime x. I have written 3 equations, 1, 2, and 3. All of them are calculating the same f prime x. Okay, 1 and 2 are using the forward difference scheme and the backward difference scheme. And equation number 3 is computing the same f prime x using the what is called the central difference scheme. Okay, now these 3 schemes are not equal. Equations 1 and 2 are kind of equal in terms of the error, right? But equation 3 is slightly better than both equations 1 and 2 in terms of the size of the error. Okay, anyway, I'll leave that as a separate assignment for you. Okay, anyway, now what if I do a plus b instead of a minus b? What if I do a plus b? What will I get then? If I do a plus b, the left hand side you will have f of x plus delta x plus f of x minus delta x. Okay, and then here these two terms will get added, f of x plus f of x, so you'll get 2 times f of x. These two terms will cancel each other out. Yes, this has a positive sign, this has a negative sign. So when I add these two equations, those two terms will cancel each other out. The next term will be, again, it's f double prime x delta x square by 2 factorial plus f double prime x delta x square by 2 factorial. So when you add them, you'll get 2 times f double prime x into delta x square by 2 factorial. 2 factorial is 2, so that 2 will cancel out. The 2 in the numerator will cancel out with the 2 in the denominator. So you'll be left with an equation that looks like this: f double prime x equal to f of x plus delta x minus 2 times f of x plus f of x minus delta x divided by delta x squared. It's not delta x square, it is delta x whole square. Okay, so please be careful when you're writing that. Okay, so this is what we are going to exploit when we write the equation for the advection dispersion equation. When we write it in the numerical form, right? The equation that we had was written in the partial differential form. Now we are going to convert it into a numerical equation. You'll understand what I mean by numerical equation maybe in the next few minutes. Okay, any questions so far before we move ahead? Anybody has any questions? It's fairly straightforward. Nothing much to worry about. Okay, again, it is not my intention that you try to memorize all of these things. Okay, it's not required for you to memorize all this. Okay, anyway, but it's important because it's very fundamental, basic stuff for anybody who wants to understand this groundwater hydrology and so on. Okay, so now what I'm going to do is I'm going to exploit whatever I've written on this screen, on this slide. I'm going to use it in the next slide. Okay, so now what I'm going to do is I'm going to come up with a numerical solution for the advection dispersion equation using what I refer to as the explicit scheme. Okay, so what we'll do is I'm going to take a domain. Okay, remember I have a one-dimensional problem. Okay, the equation has one dimension in space, and okay, so let's say this is x equal to 0 and this is x equal to L. Now remember, the original problem uh, gave the boundary condition at x equal to 0 and x equal to infinity. But because we can't really simulate infinity in a numerical sense, what we do is we just take some large value of L, okay? And then, so this becomes my domain. My domain of interest starts at x equal to 0 and ends at x equal to L, not at x equal to infinity. But we have to make L sufficiently large. I can't make it too small. Okay, I have to make it sufficiently large. How to make it large is again another matter of uh, you know, you learn it from experience, and of course there's obvious ways of figuring out whether it's large enough or not. Anyway, okay. So let us say I take a sufficiently large domain. Okay, the first thing I do is I break this domain into smaller pieces. Okay, so let me do that right now. I'm going to break them up into equally spaced boxes. Okay, I'm going to try to make it as equal as possible. So let us say I've broken it up into from let's say uh, we'll do the numbering in terms of I. So this is I equal to 1, 2, 3, and so on. And this is box number n. Okay, so the domain has been divided into n number of boxes of equal size. Okay, so let's say if you pick any random box in the middle, this is the ith box, this is the I plus 1th box, and the previous one is the I minus 1th box. Okay, so that's the general nomenclature. Now remember, what is the equation that we are trying to solve? We are trying to solve this equation, dou C by dou T equal to minus Vx dou C by dou X plus D times dou square C by dou X square, subject to the initial condition. What was the initial condition? C for all x at time t equal to 0 is equal to 0. That's the initial condition. And the boundary condition, C at x equal to 0 for all time t is some value C naught. This is the first boundary condition. And C at infinity, now in this case, I don't have infinity, I only have L. So I'll say L comma t equal to 0. These are my boundary conditions, which means even before I start solving this problem, right? So I have broken up my domain into these n number of boxes. But by virtue of my boundary condition, I already know what the concentration is at the source at x equal to 0. This box represents x equal to 0. This box represents x equal to L. Okay. So although I broke it up into n number of boxes, because I have boundary conditions where the concentration is specified, right? So therefore, I know the concentration at box number 1 and at box number n. Okay, which means the unknowns are box number 2, 3, 4, 5 up to n minus 1, right? So although there are n number of boxes, the number of unknowns is n minus 2, right? Because box number 1 and box number n, the concentration is already known. At box number 1, the concentration is C naught. That's the input concentration. Oh, remember the flow is from left to right. Okay, I didn't mention that. Let's assume that the flow is going from left to right, and therefore x equal to 0, the input concentration is C naught. And at the downstream end, at the infinite boundary, which we are calling the x equal to L, there the concentration is 0 for all time t. Okay, so now this is the setup of my problem. Now, if I want to write this, advection dispersion equation for the ith box in this uh, let's just pick this box. Okay, so let's say so this is my box. This is my box of interest. Okay, I'm going to color it with blue. This is my box for which I'm going to write the equation dou C by dou T. How will I write dou C by dou T for the ith box? Can anybody tell me? Remember, just go back one slide. and you have, okay, here I've written f of x plus delta x. It could easily be f of t plus delta t also, right? This is generic. I've just written x. Don't assume that x only means x. It can be y also, it can be z also, it can be t also. So f of t plus delta t equal to f of t plus f prime t into delta t by 1 factorial, and so on, right? So you remove x and put any other variable there. The same, see, this is a generic expression. You can take this and fit it to any generic uh, variable, right? It need not be x, it can be time also. Okay, so if I want to write dou c by dou t for this ith box, okay, I will write it as ci at t plus delta t minus ci at t divided by delta t. Does everybody agree with this way of writing dou c by dou t? It is the concentration in the ith box at time step t plus delta t minus the concentration in the same box at time t divided by delta t. This is a representation of dou c by dou t. Does everybody agree with that? Okay. I can also write it as, see, this is one way of writing it. I can also write it in this format: c of I at t minus c of I at t minus delta t divided by delta t. This would also be an acceptable way of writing it, right? So which means you know the concentration at previous time step, you are trying to solve the concentration at the current time step t. Or you can say, I know the concentration at time step t, I want to find the concentration at time step t plus delta t. So the first equation that I've written, that is more commonly used. So there's no difference between these two conceptually, but this is kind of more conventionally it's been used. So I will use the first equation. Okay, there's nothing wrong with the second equation as well. Okay, all right. Okay, so my first equation is taken, I'm sorry, the left hand side, first term is taken care of, equal to minus Vx. Now minus Vx, it's a constant velocity. I can't do anything about that. How do I write dou c by dou x now? Anybody would like to volunteer? Let me just go back one slide. Take a look at what you've written here. So how do I write this dou c by dou x? Anybody would like to say? Let's see who's in the class. Purnima is there. Purnima? Raish, you have to get the microphone to her. Do I have to say this? Wow.
Sir.
Yeah. Purnima, would you like to try? Purnima is there. Go ahead.
Concentration at x plus delta x minus concentration at x by delta x.
Okay. So now instead of perfectly correct answer, so I have to write it in terms of I. Okay.
C
Ci
C
plus 1 minus Ci. Okay. So x plus delta x is I plus 1 and x is I. Okay. Yeah. Thank you. So I will write it like this. C at I plus 1 minus C at I divided by delta x. Okay. I will leave it as it is right now. I'll come back and I'll make a minor change to this. Whatever I written is correct, but I'm going to add some more detail to it. So, but let's keep it as it is right now. Plus D Now the second term that I have has a dou square c by dou x square, which, if you notice from the previous slide, is the second derivative. F double prime x is f of x plus delta x minus 2 times f of x plus f of x minus delta x divided by delta x square. Okay, so in this case, what I'll do is I will edit as follows: ci plus 1 minus 2 times ci plus ci minus 1 divided by delta x square. Okay, now the way I have written this equation, it is it's not clear how you will solve this. Okay, but I have written one word at the top, a couple of words: explicit scheme. Now the explicit scheme is a simple scheme used for solving these types of problems. And what is typically done is, now on the left hand side, I have written two indices for the concentration, C, and then there's a subscript which is I, and then there's a superscript which is T plus delta T. And then the second term is again Ci, I is at the subscript, the superscript is T. Now the terms that I've written on the right hand side, I have only written Ci plus 1, Ci minus 1, and so on. I have not mentioned the time there. What should I mention for the time? Should I mention t, or should I mention t plus delta t, or what should I do? Okay, so the explicit scheme, what it does is it assumes that all these values are at time t. Okay, so I'm going to add the superscript to each of these different terms. Now when you look at this equation, okay, how many unknowns are there and how many knowns are there? Let us assume that Vx is known. Let us assume that Vx is known, B is known, delta x is known, delta t is known. Okay, those fundamental parameters are all known. Okay, I have Ci at t plus delta t, Ci at t, Ci plus 1 at t, and Ci minus 1 at t. Okay, these four variables. Okay, out of these four, okay, is it four? 1, 2, 3, 4. Yes. Out of these four, only one is unknown. Only one is at time step t plus delta t. Everything else is at the current time t. Right? So if I know the value at time, if I'm starting this problem to solve this problem from time step t equal to 0 onwards, at time step t equal to 0, I know the initial condition, the concentration is 0 everywhere. Right? Look at the initial condition right here written on top. Initial condition is C at x comma 0, which means for all values of x at time t equal to 0, the concentration is 0. Right? So therefore, I know all the values, all the concentration values at time t equal to 0. Right? So which means all the terms on the right hand side are known. On the left hand side, I have only one unknown, t plus delta t. So I can solve for this one equation, one unknown, solvable, fairly straightforward, right? So I can write this equation. So I wrote this generally for some ith cell, but I can write this from I equal to 2 to I equal to n minus 1, and I just keep solving this equation, right? I will solve this for the first time step. When I start off t equal to 0, t plus delta t is the only unknown. So I will solve for t plus delta t. Then I go to the next time step. When I go to the next time step, t plus delta t will become t, and t plus 2 delta t will become the next t plus delta t, right? So it just keeps going. You can march forward in time. Okay. So at every time I go from one time step to the next time step, I have to solve n minus 2 number of equations, and these are simple algebraic equations, right? The right hand side can be computed from the values from the previous time step. Everything on the right hand side is known using values from the previous time step. And then the left hand side, I have only one unknown, one equation. Okay, but I'll have n minus 2 number of such equations. So I'll solve n minus 2 equations and then go to the next time step, again solve n minus 2 equations, and so on. I keep solving it. So I can solve for, so I will solve for Ci at t plus delta t, which is the only unknown in this equation. If you have questions, please stop me. Does this make sense? It's not too hard. I'm assuming that this is straightforward enough. Too easy, huh? Okay. Yeah. So then this scheme is called the explicit scheme. Okay. Now, if there is something that's explicit, then there must be something else which we will refer to as the implicit scheme. Now, the implicit scheme is exactly the same as the explicit scheme, except for one crucial difference. So I'll just write out the whatever we had written in the previous slide. I'll write it out again here. Ci t plus delta t minus Ci t divided by delta t equal to minus Vx. The left hand side is the same. Ci plus 1 minus Ci divided by delta x plus d Ci plus 1 minus 2 Ci plus Ci minus 1 divided by delta x square. Right? Now, up to here, everything is same as the explicit scheme. In the explicit scheme, what did I do? I just replaced, I just mentioned time step values as t for all the terms on the right hand side. On the left hand side, I had t plus delta t and one value of t. Okay. Now, in the implicit scheme, what I do is I just mention t plus delta t here for every single value. T plus delta t, t plus delta t, t plus delta t. Now suddenly, what I have done here by doing this, in this equation, how many unknowns do I have? At t plus delta t, I don't know the concentration anywhere, right? So in this one equation alone, I have Ci minus 1, Ci, and Ci plus 1, all of them at t plus delta t. So in this equation, there is only one known, which is this term here, Ci at t. All the other terms are unknown. Of course, Vx and d and delta x and delta t, those are known. Apart from that, all the other terms are unknown. So what do I do? Any thoughts? Okay, I will what I'll do is I will collect all the t plus delta t terms on the left hand side, and there's only one other term which doesn't have t plus delta t, which is the CIT. This term over here on the left hand side, which is currently on the left hand side, I will move that to the right hand side. Okay, so let me try doing that. I want to collect all the terms Ci minus 1 t plus delta t. How many terms have Ci minus 1? There is only one term. This term over here, Ci minus 1 t plus delta t, has got a coefficient of d divided by delta x square. So if I bring that over to the left hand side, it will have a coefficient of minus d divided by delta x square. This is the coefficient of Ci minus 1 at time step t plus delta t. Now let me write the Ci term. at t plus delta t. Now this term has got, oh, sorry, I forgot to do something. I'm going to multiply, so I'll just write d into delta t over here. I'm going to multiply both sides by delta t. Okay, so the delta t in the denominator will disappear. Okay, so that's why I'm getting d into delta t divided by delta x square. Okay, so now ci at t plus delta t will have a coefficient of 1, which is the term on the left hand side, which is already on the left hand side. I'm going to keep that as it is, 1. Then I have this term over here, ci at t plus delta t has got a plus vx by delta x into delta t. Okay, but when it comes over to the left hand side, it will become minus vx into delta t divided by delta x. Okay, so this is the ci term from here, and then I have another ci term here. It has minus 2d delta t by delta x square. When it comes over to the left hand side, it will become plus 2d, so it will be plus 2d times delta t divided by delta x square. This is the coefficient for the term ci at t plus delta t. Okay, the algebra is not hard. Okay, you can always figure this out without too much trouble. If you just sit down quietly by yourself and do it, you will get it. So I'm not going to worry about, and of course you don't have to memorize all of this, so don't really worry about it. Okay, so this will be vx times delta t divided by vx times delta t divided by delta x uh, minus d delta t divided by delta x square. So all this complicated stuff on the left hand side, I have moved all the unknowns to the left hand side. On the right hand side, I'll have a very simple looking equal to ci times ci at times step t. That's it. So I have first equation had unknowns and knowns on both sides of the equation. Now I have collected all the unknowns on the left hand side, and the solitary known has gone to the right hand side. Now what I'll do is I will write this equation. Now you will notice that the terms that are inside the parenthesis, inside the brackets here, minus d delta t by delta x square, 1 minus vx delta t by delta x plus 2d delta t by delta x square, vx into delta t divided by delta x minus d delta t by delta x square. These terms, for a particular problem with a certain value of vx and a certain value of d, and if you fix delta x and delta t, whatever is inside these brackets is a constant. Agreed? So it will be some constant a times ci minus 1 plus, okay, maybe so a1, let's call it a1. a1 times ci minus 1 plus a2 times ci plus a3 times ci plus 1, all of them evaluated at t plus delta t, equal to, so I can write it like this. Okay, so some constant a1 times ci minus 1 plus a2 times ci plus a3 times ci plus 1. All of these are evaluated at t plus delta t. Please keep that in mind. Equal to ci at t. Now, if I write this equation, now look at this equation. This equation has three unknowns, but there's only one equation. Okay. Suppose I write this equation from I equal to 2 to I equal to n minus 1. Remember, I equal to 1 and I equal to n, I already know the boundary conditions are already known. So if I write this equation for I equal to 2, for I equal to 3, for I equal to 4, and then so on up to I equal to n minus 1, then I will get a matrix, a system of equations. I'll get a system of linear equations or simultaneous equations, n minus 2 simultaneous equations that I can solve using, a matrix method. Does everybody agree with that? So what will happen is you will you will you will you can write this whole thing as a as a system of simultaneous equations, right? So it will be a, so from I equal to 2 to n minus 1, you will get a system of simultaneous equations. How many equations will you get? You will get n minus 2 number of equations, right? From 2 to n minus 1, if you write for each value of I, you will get n minus 2 number of simultaneous equations. Now it's totally possible to solve such a simultaneous equation, right? So it's what you will get. Okay, actually, maybe I'll try to explain that in the next slide. Okay. So I will write it for cell number I equal to 2. So it will be C2 at t plus delta t times some constant plus C3 at t plus delta t times some constant, whatever that value is, 1 minus Vx and so on and so forth, equal to C2 at t. Remember, just go back to the previous Ci at t, which is C2 at t, and then there will be a C. So there should have been there should have been a C1 here, right? T plus delta t. Remember, this is the for I equal to, for I equal to 2, you will have I minus 1, I and I plus 1 terms. Okay, so the C1, what is special about C1? Concentration at the source at x equal to 0 is always known. Is it an unknown? Ci at t plus delta t is not an unknown, so it can be moved to the right hand side. Okay, so what I'll do is I'll just erase this from here. This term for this particular, for cell number 2, it becomes a known, and it can be moved to the right hand side. So it will be minus C1 at t plus delta t times whatever constant, right? That will be some negative number anyway. Okay, then I'll write this for C3. So it will be C3 at t plus delta t times some constant plus C4 times some constant at t plus delta t. And then there'll also be a C2 term, right? C2 at t plus delta t times the constant. For all other equations, for all other values of I greater than 2 and less than n minus 1, I will get 3 terms on the left hand side and only 1 term on the right hand side, right? And so on. So this will go on. This will go on. The nth equation will have C, sorry, the n minus 1th equation. And what will happen to the n term? That will again go to the right hand side because that is known. The concentration at x equal to L is always known. So it's 0, right? So it just goes to the right hand side. So I'll have Cn minus 1 at t plus Cn at t plus delta t times whatever that constant comes out. So if I write this in matrix form, I will get what are the unknowns? The unknowns are C2, C3, and so on up to Cn minus 1. All of these are evaluated at t plus delta t equal to the right hand side. Okay, I'm not filling out all the values, but what will happen is in the first row, what will I have? I will have these two coefficients, and all the other coefficients will be 0. In the second line, I'll have the coefficient for C2, C3, and C4, and then everything else will be 0. In the third row, I will have the coefficient for C3, C4, and C5, and everything else will be 0. So you will have, this is the diagonal terms, there will be what's called a tri-diagonal matrix. Tri-diagonal matrix. right? So you will have all the terms along the diagonal, one above and one below. So you must have done this if you've taken a math course, linear algebra or something like that. You would have done this. What is that? Lower triangular matrix, upper triangular matrix, LU decomposition, and so on. If you have not done it, just go online and search up what a tri-diagonal matrix is and how to solve those kinds of systems or equation. Basically, there are many algorithms available. So how to solve this equation? You just invert the matrix. So this equation is of the form ax equal to b, or in this case a into c equal to b. So the solution is c equal to a inverse b, right? C is the solution that you want. I want to know the concentration C2, C3, C4 up to Cn minus 1. So how to do it? Just take this tri-diagonal matrix, take its inverse and multiply it by the right-hand side vector, and you will get the concentrations in all the um, um, uh, in all the cells that you have that you have broken up your domain. Basically, the first step that you do is you take your domain and break it up into small boxes of equal sizes, okay, of equal constant delta x, and then you set up the equations to solve it. Okay. Now you might be wondering, why should I do all of this difficult stuff if I can just do the explicit scheme, right? In the 2 slides back, we wrote the explicit scheme where it was just a simple algebraic equation. You can just solve it and then be done with it. Now this implicit scheme seems to be much more complicated and pretty unnecessary, right? Well, there is a reason why we do all this. It is, although it looks unnecessary or it looks complicated, the problem is that the explicit scheme is not stable always. Okay, you have to satisfy some stability criteria to ensure that the scheme will give you more or less reasonable answers. If you're uh, uh, basically what that means is that the delta t that you can use for the explicit scheme has got to satisfy some criteria. You cannot use any value of delta t. If you use any value of delta t, the solution may blow up. The solution may not be reasonable at all. It may give you incorrect answers. It might give you numerical, what are called numerical oscillations, and so on. Okay, so basically the disadvantage of the explicit scheme is that it is not unconditionally stable. Okay, the explicit scheme has an advantage in that it is simple to solve, right? You can solve it by hand pretty much. Okay, I mean, I'm exaggerating a little bit, but it's an algebraic equation. Okay, it's the computational cost of solving the explicit scheme is very low. It's not very expensive. When I say expensive, I mean amount of computations required are relatively low. Okay, it's easy to solve this. Okay, they're just algebraic computations, and then you solve for Ci, right, in the explicit scheme. But in the implicit scheme, the advantage is that it is unconditionally stable. You can use any value of delta t, and you can solve the problem. Okay, so that is why we have these two schemes. The explicit scheme, the advantage is that it is simple, easy to solve. The disadvantage is that it is not unconditionally stable. The implicit scheme, on the other hand, the next one, the one with this tri-diagonal matrix and all that, it is unconditionally stable, but the disadvantage is that the cost of computation is higher. Okay, there's always benefits in using a simple approach versus a slightly more sophisticated approach, which requires some additional cost in terms of the computational cost, but it gives you an advantage in the sense that it's going to be stable. The answer that you get from the implicit scheme is unconditionally stable. So that's the comparison between the explicit scheme and the implicit scheme for the numerical solution of the advection dispersion equation. Okay, so the condition for stability, I've just written it over here. For the explicit scheme, it is stable only if the time step delta t is less than or equal to delta x divided by 2d divided by delta x plus v. Again, okay, so this should be vx. I'm sorry, I've used vx everywhere, so this should be vx, the velocity in the x direction. Okay, So this is the condition for the stability of the explicit scheme. The implicit scheme, as I said, is unconditionally stable. Okay, so unless if you are using the implicit scheme, you don't have to worry about the time step. You can use any time step you want. But if you're using the explicit scheme, you have to check whether the time step is below this number. You compute this number, whatever you have, and check whether your delta t is less than that. If it is not, then your solution will be incorrect. It will start to give you unreasonable answers. Okay. Okay. We will stop with that. I think we are out of time. Okay. Did you guys get a chance to look at the what is that? The problem statements that I sent out? I probably sent it out maybe a few hours back, maybe 5 6 hours back, early in the morning for you guys. Did you get a chance to look at it? Anybody? Any questions on that? Yeah, you have to look at it to have questions. So yeah, try to take before we meet next time on Tuesday. Please. Oh, there are questions. Very good. Unmute, Raish, please.
So the email says there will be argument between groups at a time. Like, can you explain that format, please?
Uh, there will be an argument between the groups. Argument as in not
Debate or like what? Project discussion.
a scientific argument. So you will say, so let us say you are arguing for a particular side. You will have to give scientific, logical reasons why you think your client is right or wrong, whatever it is, right? Your client is not wrong, or why you think your opponent is wrong. Okay. And then after you finish, your opponent will present their case and to indicate why they are correct and you are not correct. And then you'll get a chance to do a 2 minute question and answer session kind of thing. So you will say, hey, your this assumption is wrong, or you did this incorrectly. And then they will also get a chance to do the same thing to you. You have to answer the questions from the opponent. It'll be fun, I promise. Assuming all of you turn up.
Okay.
Okay. So basically, you have to be prepared to defend whatever assumptions you have made. Okay, let's say you assume some hydraulic conductivity, or you have assumed some porosity, or you have assumed some pumping rate, or something, whatever you have assumed, because the problem doesn't tell you what to assume. You have to see the Python code that I've given has put in certain values of. Okay, so the just let me finish. The Python code is a generic code with some numbers in them. You have to decide what numbers to put in for the different parameters, such that it supports your argument. Whatever argument you are going to be presenting, you should put in the numbers appropriately in the Python code to support your argument. Okay, and use that as your defense. And you'll have to poke holes in the opponent's argument. Yeah, go ahead, Anvesha.
So which group is arguing on which side? It's not clear.
It's mentioned in the email.
So, but the PDF you send, some of the problem statements are like you have to argue on side A slash side B, side B.
Really? I don't think so. 1 second. Let me just. So in problem one, you have the even numbered groups will, for problem one, they will argue on the side of the village. Okay, which means the other odd numbered groups will have to argue against the village. I think it's in that case it's the industry. Similarly, in problem two, it's the industry versus, what is it? Industry against somebody. I forgot now what problem two is. Just a second. In problem two, oh, it's the farmer versus the industry. In the first case, it's industry versus village. In the second problem, it's industry versus farmer. In the third case, it is industry versus the pollution control board. And in the fourth case, it's the Department of Environmental Protection versus industry. So I think it's fairly obvious. If you still have doubt, we can discuss it again in next class. Okay. All right. Thank you very much. Take care. See you all on Tuesday. Has the rain stopped? Stopped raining?
So for now, yes.
Okay, good. The ponds are full, I suppose.
Yes, sir.
Okay. All right. Take care, guys. See you on Tuesday. Bye bye.